In this video, we will study what is an Argand diagram and how is it linked to complex numbers. We know that a normal grid is labeled as x-axis, y-axis, and this is known as the Cartesian plane. This is used for real numbers. Then the question is, what is an Argand diagram? An Argand diagram is technically the same thing as a Cartesian plane, except Argand diagram is used for complex numbers. If z is written as x plus iy, a complex number has a real part and an imaginary part. So we also write this thing like this. Real part of the complex number z is x and imaginary part of the complex number z is y. So when we have to plot complex number on the grid, we now call this diagram as the Argand diagram. The x-axis is now labeled as the real axis and the y-axis is now labeled as imaginary axis. So now what we will do is that we will plot different points on the Argand diagram. Let me first label the y-axis as imaginary axis, the x-axis as real axis. This point is the origin. I'm given a complex number z, which is 4 plus I. Another complex number w is given, which is 3 plus 3i. Let's add both of them. So z plus w is added. 4 is added to 3, the real with the real, and the I is added to the I, the imaginary with the imaginary part. 4 plus 3 becomes 7 and I plus 3i becomes 4i. So now we have z, which is 4 plus I. Now we have w, which is 3 plus 3i, and we have z plus w, which is 7 plus 4i. Now let's plot these points on the Argand diagram. So 4 plus I is like the coordinate 4, 1. So this is 1, 2, 3, 4, 5, 6, 7. I'm labeling the x-axis. I'm labeling the y-axis with I for the imaginary part. So this is I, 2i, 3i, and 4i. Let me first plot the point that is 4 plus I. So this is 4 from here. This is I from here. So this is the point. Let me label it by the alphabet A. Now let's move to w. W is 3 plus 3i. So this is 3. This is 3i. So 3 plus 3i is over here. Let me label it by the alphabet B. So what I can do now is that I can draw two lines from the origin. The first line I'm drawing, it's from O till A, and I'm labeling this point as A. The second line that I'm drawing, that is from O till B. This is like a vector. So OA is a vector, OB is a vector. And what is the third point? That is 7 plus 4i. So this is 7, this is 4i. Let me label 7 plus 4i over here. Let me label this thing as C. And let me draw a line from origin till C, that is this point. So now I have labeled this as C. Now look at all the vectors. I have OA, I have OB. This is like a parallelogram of vectors. I have added the vector OA plus OB. What do I get? I get OC. That means if I were to complete this parallelogram, how would this parallelogram look like? From B to C, I will join it by a line. Similarly, from A to B, I'll join it by a line. So therefore, if I label it properly, this vector is like this vector. So these two are parallel vectors. Similarly, this vector is like this vector, and this is like addition of two vectors on an Argand diagram. So the Argand diagram helps us to visualize complex numbers as vectors. Let's move to another example. This time I have the complex number z given as 2 plus 3i. The complex number w is given as 4 plus 2i. This time I am doing the subtraction z minus w. So 2 plus 3i, this is z, minus 4 plus 2i. So this is 2 plus 3i minus 4 minus 2i. So the 2 and the 4 subtracts and gives us negative 2. The 3i and the negative 2i subtracts and we are getting a plus I. So now let's apply the same strategy as before. Let's label this thing as A. Let's label this thing as B. And let's label the last one as C. And now we are labeling the x-axis as the real axis, y-axis as the imaginary axis. Origin is still the origin, and this is an Argand diagram. So the first point is 2, 3. So let me label the x-axis 1, 2, 3, 4, 5 and I, 2i and then 3i and 4i. So now I'm labeling the first point, that is 2 plus 3i. So this is 2, this is 3i. So that point is over here. I'm labeling it as A. And I'll also join it from the origin and I'll make it as a vector OA. That is the first thing. The second point that I'm labeling is 4 plus 2i. So this is 4, this is 2i. So this is 4 plus 2i is over here. This is the point B. And again, I'm drawing a vector from origin to the point B. This is the position vector. And the third point, that is minus 2 plus I. So negative 1, negative 2, this is negative 2, this is I, that's right over here, that is C. And let me draw a vector also over here. So this is from origin till C. So this is the third vector OC. So now this is like the subtraction of two vectors. That means this vector Z minus the vector W is giving me this vector. Why? Because this vector will be in the opposite direction over here. Let me show you a rough diagram. So therefore this B would be somewhere over here in this direction, and that would be negative B. And then when we add the two vectors by drawing a parallelogram, something like this, and this is what we are getting. So another graphical representation of vectors on the Argand diagram. Now let's move to another grid. This time I'm writing a complex number Z as 3 plus 2i. And we know that the conjugate of Z is 3 minus 2i. The sign of the imaginary number changes. Now let's plot on the Argand diagram. I have labeled the x-axis as real, y-axis as imaginary. This is the origin. This point I'm labeling it as A, and this point I'm labeling it as B. Now A is in the first quadrant. So 3 plus 2i. So this is 1 and 2 and 3 and 4. And this is I and 2i and 3i. And this is negative I, negative 2i, negative 3i. So let's label A. That is 3 plus 2i. That's over here. This is A. And I'm drawing a vector once again from origin till A. Similarly, I'm labeling 3 minus 2i. The x coordinate is the same and this is minus 2i. So this goes over here. This is the point B. And again, I'm drawing a vector from origin till B. What do I observe? I observe that if two vectors are conjugates of one another, they are reflection of each other in the x-axis, which is now known as the real axis. So what else do we observe? We observe that the length of this vector and the length of this vector is the same because the coefficients are the same, 3 and 2, 3 and minus 2. the length of the vector according to the distance formula or according to magnitude of vector is exactly the same. Now let's label another pair of complex number. Let me take z as -2 plus 3i and z star is -2 -3i. Again, the sign of the imaginary number changes and naturally it will be reflection of each other in the horizontal axis, which is the real axis. Now let me label the points. We have -2 plus 3i. So this is -1, this is -2, this is I, this is 2i, this is 3i, -i, -2i, -3i. What else needs to be labeled? The real axis, the imaginary axis, and the origin. Now let me label the first point as A. So we have -2 plus 3i. So this is the point and this is A. And now I'm drawing a line from origin till point A. This is the vector OA. Now let's label z star, z conjugate as point B. The coordinates are -2 and -3. So this is -2, this is -3, this is labeled as B, and I'm again drawing a vector from origin till B. So this is the vector OB. We have already seen that the two vectors are reflection of each other in the real axis. It does not make a difference which quadrant they belong to. A is in the second quadrant, its reflection is in the third quadrant. Similarly, in the previous example, A was in the first quadrant, its reflection is in the second quadrant. It could be in the second quadrant, its reflection will be in the first quadrant. Again, over here, the original complex number could be in the third quadrant, its reflection will be in the second quadrant. So what have we learned in this video? We have learned that complex numbers are labeled on a diagram, on a grid, which is now known as Argand diagram. And the x-axis is now labeled as the real axis, y-axis is now labeled as the imaginary axis. We will plot the points just like on a normal grid. We convert the complex number into coordinates and we plot it. And we have drawn vectors with respect to origin also. They are labeled as, they are known as position vectors. And that's the basic knowledge that we have learned in this video.